Okay, good afternoon, everybody. It's 12:15, so we can start our lecture right now. I can see that most of us are already here. I can see 10 participants. Can you hear me all right?
Yes.
Yes.
Okay, thank you so much, because we are doing it the first time from home. You know the reason why, just in case. Well, it's going to be quite a challenge for me, because without slides and without a blackboard, I will have to struggle with Adobe, and I'll have to alternate between whiteboard and this printed file. However, I did some tries and it more or less worked, but please forgive me any awkwardness, because I'm doing it the first time in my life, and I don't know how it will work out. I'll do my best. Anyway, whatever I tried, when I tried just to use a whiteboard, then I cannot write with a pen, only with my finger. And then this is horrible, that my handwriting is almost illegible. Then, of course, I'm not going to spend so many hours preparing slides for each lecture. So this is also out of the question. Then I thought, well, I have a genuine whiteboard at home. So I could just write on the whiteboard and have it on the camera, but I couldn't position my laptop in such a way that the camera would really screen appropriately the whiteboard. So at the end of the day, I decided to use a PDF file of the lecture notes and do appropriate highlighting and annotation. So I hope it will work. Okay, so now let's get to work. Remember, last time we proved a theorem that told us that the space of all finite paths in a graph is finite itself if and only if there are no loops. Okay, and here one of the main points was that no matter what kind of graph we have, if we fix the length of a path, there are no, and we have n edges, then we have at most n to the power k different paths of length k. And this is regardless of whether we have loops or not. But this is a very big number. This is not an optimal estimate. So what we are going to do today, that's the whole point of today's lecture, is to improve this estimate. And now let's see if the highlighting works. Okay, and now I can highlight it. So the point of today's lecture is to have this estimate better, to make it optimal. So our goal is to find the optimal estimate for all paths of length k in a graph which has n edges and no loops. Because remember, the moment we admit loops, then we can have this Hawaiian earring diagram, and then indeed this estimate n to power k is optimal. So in order to have a smaller number, more interesting combinatorics, we must disallow loops. Okay, and this is what we are going to do today, to disallow loops and see how we can improve an estimate for the number of all paths of length k in a graph without loops with exactly n edges. All right, and to begin with, we will prove this theorem. So first I have to delete it now. Okay, now I highlight the theorem. Okay, and the theorem says, let E be any graph if there is a path P that is either finite or infinite, but only in one direction. So we don't admit paths which are infinite in both directions, so labeled by integers. We admit only paths that are finite or labeled by positive natural numbers or negative natural numbers, and whose edges can be non-trivially rearranged. So if you want to permute it into a path, then there exists a loop. So in other words, what we want to obtain is, if there is no loop, then you cannot rearrange edges in a path into another path, right? If that would be possible, then we would definitely have a loop. So this is a general theorem which I like quite a bit, and the proof is very much similar to one of the exercises we already had. I don't remember who was solving it, maybe Jacek, I don't remember. Never mind, it doesn't matter. Okay, but first, for starters, I want to reduce the problem to something slightly simpler. So what we observe to begin with, okay, sorry, I told you it will be a bit awkward, but I'm trying. Now let's highlight the first sentence. Well, I guess if I were writing it on the blackboard, it would take even longer. Yep. So for starters, we note that if we have a path that is infinite in one direction, then this is exactly a path which is infinite in the opposite direction in the opposite graph. Remember the definition of the opposite graph? I can try to pull it out. Should be somewhere here. Yes, definition 1.2. The opposite graph of E is a graph which has the same set of edges, the same set of vertices, but we swap the source and the target map. So now the target map is the source map and the source map is the target map. So to put it more vividly, what we are doing, we're just reversing the orders of all arrows. So where was a beginning, there's an end, where there's an end, there is a beginning, okay? So this is pretty clear that if we take a path which is, say, infinite to the right in a graph E, then the same path will be infinite to the left in the graph E op. Okay, and now I remember I could do the following. Yes, I could write it. So for instance, if we have an infinite path of the following form, E sub 0, E sub 1, E sub 2, and so on and so forth to infinity. And this is in the graph E. Then when we pass to the opposite graph, now this path will become the following. Will come from minus infinity, and we will have an edge E minus 2, minus 2, E sub minus 1, and E sub 0. Right? I hope you can see it, because now the beginning of E0 is actually its end. So it must be the beginning of E1, but the beginning of E1 is exactly the end of E minus 1, and so forth, so on and so forth. Right? So by reversing the direction of the arrows, an infinite path which is escaping to plus infinity from a given start is actually escaping to minus infinity from the given end. Okay, so that's our first observation. And well, okay, then we delete it. How do I delete it? Wait a second. Delete. I want to delete the highlighting. Okay. What we observe next, that a non-trivial permutation of edges in the path in E is tantamount to a non-trivial permutation of edges in the same path considered as a path in the opposite graph. And again, let me write the following simple formula to convince you. You see, if F is, say, the permutation of natural numbers, which means a bijection from n to n. Okay, n to n. So now if we want to derive from it a bijection from minus n to minus n, there is an obvious formula for this. So now it goes from minus n to minus n. And we can define it as follows. G of I. Oops, what happened? Okay, G of I is by definition, I warned you it's not going to be completely smooth, but I'm trying, equal to what? To minus F of minus I. So you see, it makes perfect sense. If I is a negative natural number, negative non-positive integer, if you want, then minus I is a natural number. So f of minus I is a natural number, and minus f of I is in the set minus n. Okay, and now it's obvious that f is non-trivial if and only if g is non-trivial, and obviously you can solve this equation, and this formula is completely equivalent to writing that f of j is equal to minus g of minus j, right? Because this is the way we match up a path indexed by n with a path indexed by minus n, exactly by reversing the signs. Okay, so you see, if you have a non-trivial permutation of a path in E, and then you consider this path as a path going in the opposite direction in E op, then any non-trivial permutation, rearrangement of indices in E of this path is tantamount to a non-trivial permutation or rearrangement of edges in the opposite graph. Okay. Well, again, it's pretty clear that if now I should be able to delete it. Delete. That a loop in E is also a loop in E op, because if we reverse just the direction of the arrows, well, we don't change the fact that a given path which was a loop is still a loop. Yeah, let me write it down in the following way. So if I have a path in E which is a loop, then what does it mean? It means that the source of P is equal to the target of P. But now if we consider this path in the opposite graph and look at its source and its target, the source of P is exactly the target of P opposite. So in other words, T op of P op is equal to S op of P op. Right? This is because T op of P op is exactly S of P, and S op of P op is exactly T of P. So if these two guys are equal, also these two guys are equal, which means that this path considered in the opposite graph is also. All right? Okay, but now we have established some important logical equivalence. Namely, we can now claim that if we assume that having a path, say, going to plus infinity in E, if we assume that having such a path that can be non-trivially permuted into a path in E implies that there's a loop in E, then having sorry, I got confused. Yeah. So now, okay. So now assume that we proved in a graph E that if we handle a path going into plus infinity, if we prove a statement that being able to non-trivially permute edges of this path into another path implies that there is a loop in an E. Imagine that we have already proved it. Okay, that's if you want an assumption. And now I want to conclude that this assumption implies, in fact, that having a path in the opposite graph going into minus infinity that can be non-trivially permuted into a path in this opposite graph implies that there is a loop in the opposite graph. And that's because of these equivalences, logical equivalences that we proved. Remember that if I have an implication P implies Q, and I have that P is equivalent, say, to P prime, and Q is equivalent to Q prime, then I can also claim that P prime implies Q prime, okay? And this is exactly what I'm doing here. So first I establish that having an infinite path to the right is tantamount to having an infinite path to the left. And if this path can be permuted non-trivially into another path in E, then then the path in the corresponding path in EOP can be also non-trivially permuted into a path to EOP. And then we establish that if a path is a loop in E, then this path considered in the opposite graph is also a loop. Okay, so we have these equivalences. Therefore, if we have this implication for path going to plus infinity to the right in E, we also have an implication for paths going to minus infinity in the opposite graph. Okay, and now we get the reduction that we want. Just let me delete it. Okay, delete the comment. Okay. So therefore, we can conclude that because any graph can be written as opposite of its opposite, then without the loss of generality, we can assume that our path is either finite or has edges indexed by n. Indeed, remember, this is because the statements that we are making here are completely general. So imagine that we have already proved for an arbitrary graph that having a path going to plus infinity with non-trivial rearrangement property implies that we have a loop. Then we just argued that in this opposite graph, we will have a similar statement. But now this is for all graphs E. So imagine that for a graph E, we take the graph F opposite, where F is an arbitrary graph. So now having the statement for paths going to plus infinity in the opposite graph implies by the argument above that we have an analogous statement for paths going to minus infinity in the opposite of this graph. But this is the opposite of the opposite. So we just proved that in an arbitrary graph F, we have a desired implication also for paths going to minus infinity that can be non-trivially rearranged into another path. Okay, so this way we don't have to repeat, we don't have to study three cases in our reasoning. We just study either the set of natural numbers or a finite subset thereof. We don't have to consider yet another third case of what happens when we have a path escaping to minus infinity. You see, the crux of the argument is that we can choose a minimal element. So when you have a finite set or the set of natural numbers, there always exists a minimal element. But if we would consider minus natural numbers, then we would argue, okay, a finite set or the set of minus natural number always has a maximal element. The argument would be completely analogous, and it would be a waste of time to do it twice. So I hope this reasoning that we can reduce without the loss of generality to these two cases is convincing for you. Do you have any questions at this point? Okay, I don't hear anybody. I guess it was elementary, so let's move on. Delete the highlight. And now it's getting slightly more interesting, I hope. Oh, come on. Select two, please. Okay, so we consider a subset of natural numbers that has at least two elements. In fact, we'll be interested either in a simply finite subset of natural numbers, say from 1 to some n, or all of natural numbers. But what we are really interested in is the following general argument. If we assume that we have a bijection sigma from this subset S to itself, okay, that is not identity, then of course, because we are talking of a subset of natural numbers, there exists the smallest j, such that sigma of j is not equal to j. Such a j must exist because sigma is not identity. And because we are bounded by 0, there must exist the smallest number with this property. Okay? Now, as sigma is bijective, we claim that sigma of j must be bigger than j. Why? Well, let's see this argument. Well, first, it's completely clear that if j is already the smallest element, we are done. If j is the smallest element in our set, and a sigma of j is not the j, then it cannot be smaller than j because j is the smallest element. Okay, so now we have to consider other situation that j is not the smallest element, which means that there are some i's, indices I, that are smaller than j. But then we can draw the following conclusion. That, well, first, sigma of j is not equal to sigma of I. Well, that is clear because sigma is a bijection, so in particular it is an injection. And since I is different from j, then sigma of I must be different from sigma of j. But we also assume that I is smaller than j, and j is the smallest element for which sigma of j is not equal to j. So it means that sigma of I must be equal to I. And now it implies what we want. It implies that sigma of j is bigger than j. Well, why? Because if it were equal to I, it would be also equal to sigma of I. And it cannot be equal to itself, so it must be bigger. I think I would like to make a very simple drawing, which is very convincing. New share. Okay, whiteboard, share. Okay, so imagine that here are your indices labeled by I, which is less than j. Here I have this index j. And again, here we have these indices labeled by I. And here I have the index j. And this assignment here is our map sigma. Okay, so we look where we can map our j with sigma. Well, we cannot map it to j because we know that sigma of j is not equal to j. We cannot map it to I less than j because we already know that here the assignment goes from I to I. Here this is an identity. And because sigma is a bijection, well, this is not allowed. I cannot have j bigger than I assigned the same element as I. Okay, so this is not allowed. Now we cannot also map j to j, so the only place where we can map j is to something bigger than j. So this is, if you want, just a pictorial proof of what I wrote down formally. And as you can see, writing with my finger, well, it's okay for a simple picture, but I couldn't imagine writing full sentences in English with my finger. And my stylus pen digitizer just didn't work. Okay, now we go back to lecture notes, which means what? I have to go to new share. I go back to this, share, voila, and here we are. Now, furthermore, okay, so this we delete. Furthermore, we observe that, of course, sigma inverse of j is also not equal of j. Well, look, if sigma inverse of j were equal to j, then it would imply that sigma inverse of j, which is j, would be equal to sigma of j, but that's not the case. All right, so we also have that sigma inverse of j is not equal of j. And here's a cute little argument that in fact it also must be bigger than j. First have to delete this highlight. Okay. So now we want to exclude the situation when sigma inverse of j is less than j, but we get a very cute contradiction pretty much immediately. You see, because if we have that sigma inverse of j is less than j, then of course sigma applied to it must be just the identity, because remember, sigma on elements, on indices that are less than j is by definition identity. So sigma of sigma inverse of j is sigma inverse of j. But then we have that j is equal to sigma inverse of j, which is less than j. We get that j is less than j, which hardly ever happens. Therefore, we can conclude that also for the sigma inverse of j, that it is strictly bigger than j. Okay, and we need these estimates. So this is all revolving around an exercise which was done in our recitation class. And we need it because now knowing which indices are strictly bigger from which indices, we can arrange paths, okay? Because remember that we have it by assumption. By assumption, we have a finite or an infinite sequence labeled by natural numbers of edges with a property that they form a path. So the end of one edge is the beginning of the next edge. And then we can always slice it as long as we keep track of which indices are bigger, which indices are smaller, and arrange subpaths into paths. Okay, and now here we can do, so I didn't highlight it, so let's do it properly. So now I hope you all agree that we can draw this conclusion that also sigma inverse of j is bigger than j. Any questions thus far? I think it's pretty elementary combinatorics. Now, we can do two cases at the same time because really what we are banking on is the existence of a minimal element. That's why I couldn't handle the three cases at the same time, because if we have minus natural numbers, then we cannot argue by minimal element, we have to argue by maximal element, but we already took care of it at the very beginning. Okay, so we take our path to be either infinite to the right or simply finite. So this means that our set is either the set of all natural numbers or just a finite set from 1 to n. Okay? In particular, these two sets satisfy the property of a set S that we used above. We assume that we have at least two different indices, that we have at least two different elements in the set n, so n is at least 2. And we assume that there exists a permutation or a bijection, if you want, from S to S with a property. And this is exactly what I need to highlight right now. That when we rearrange the edges of our path according to this permutation, it is again a path. Right? So this is our assumption. But we have a non-trivial bijection sigma with the property that when we rearrange edges of our path P with respect to this sigma, so in other words, we have a path labeled sigma 1, sigma 2, sigma n, and we either go to infinity or we just stop at sigma n, that this is again a path. Right? This is our assumption. And now we want to prove that this means that we have a loop in our graph E. Okay, so first, what we can quickly note is, because of what we managed to show above, that if I take, oops, select tool, okay, highlight, that if I take a sequence of edges, ej, ej plus 1, and so on and so forth, up to E sigma inverse of j, and remember, this makes sense because sigma inverse of j, we proved that it has the property that it is strictly bigger than j, so it is at least j plus 1. So this is indeed a subpath of P, okay? But then, of course, when we apply our permutation, our bijection sigma, then by our assumption, the arrangement of edges from sigma j to j is also a subpath, but this time of P sigma, right? Because this is what happens. We apply sigma to the whole path, so it turns, and we assume that it turns a path to a path, so obviously it turns every subpath to a subpath. And by the way, I modified the definition in the lecture notes. Oops, I'm inconsistent. So here I subpath without the hyphen. I modified this definition as we discussed, and it's now written in the notes. Let me show you. And I think I did it better than ad hoc on the blackboard. Yes. So now it looks like this. Yeah. So this is this condition that there are no gaps, which we discussed so vigorously last time. Right? So not only we assume that the set of indices is a subset of the set of all indices, but we assume that there are no gaps. So if I have two indices I and j that are in j, then also every index in between must be in j. Okay? So that has been clarified. Okay, so this part is clear. Since sigma turns the whole path into a path, then also every subpath is turned into a subpath, right? And if we apply sigma to all these indices in the subpath, where indices run from j to sigma inverse of j, well, then we obtain indices that will run from sigma of j plus 1, and so on and so forth, up to sigma of sigma inverse of j, which is, of course, j. Right? So this, again, is a path, even though here we do not have that these indices as such are increasing. But this is our assumption, that if we make a rearrangement, it's still a path. Okay? Now we have to consider two cases. A very simple case, that sigma j is sort of the smallest number bigger than j, which means it's j plus 1. But then we are done. Because if sigma j is equal to j plus 1, then the path which we just considered, this path E sigma j dot 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 ej, is nothing but a path from ej plus 1 to ej, and it is already a loop, because the end of ej is the beginning of ej plus 1 by the very assumption that P is a path. So this is already a loop, and we are done. So now assume a slightly more difficult situation, that sigma j is strictly bigger than j plus 1. Then, following this path, which we just considered, with the path with edges labeled from j plus 1 to sigma j minus 1, mind you, now it makes sense, because sigma j is at least j plus 2, and j plus 2 minus 1 is j plus 1. So this is a path with at least one edge. So it makes sense. Okay. And of course, we can put it after the path which ends at ej, because the end of ej is the beginning of ej plus 1. So then we obtain the path which goes from sigma j to ej. That's the first part of the path. And then we follow with the next part, which is a path from j plus 1 sigma j minus 1. And this we know is a path. But of course, it's a loop, because no matter what the number sigma j minus 1 is, we know, because it's by assumption that P is a path, that the end of the edge labeled by sigma j minus 1 is necessarily the beginning of the edge labeled by sigma j. So this is a loop, and we are done. So this theorem is proven. we cannot rearrange order of edges in a path without creating a loop, whether this path is finite or infinite in one direction. And mind you, it is completely obvious why we have to consider paths that are infinite in only one direction, because we have an immediate counterexample. Maybe I can just okay, let me say highlight it. No, I'll do the following. Or infinite in one direction. I'll highlight this part. Yes. And now make an annotation. Because imagine that we have a path labeled by all integers, right? So we come from minus infinity, we have e minus 1, sorry, minus 1, e 0, e 1, and we go to plus infinity, okay? Then we can just take a unilateral shift, a bijection from integers to integers, which is simply defined by the formula that f of n is equal to n plus 1. Obviously, is a non-trivial bijection, all right? But when we rearrange this path with this bijection, well, we'll basically get the same path. So the path will be non-trivially rearranged, yet it will be just itself. So it definitely will be a path. And we have a graph which is just consists of this one path going from plus to minus infinity. We are done. We have no loops, and we have a path, and we have a non-trivial bijection. We rearrange this path with a non-trivial bijection, and we still get the path, and we have no loops. So this is a counterexample. That's why we cannot assume that our path is infinite in two bijections. If you remember the definition of a Teplitz algebra, then this is given by the isometry, which is given precisely by the same formula. Look, if I have this map F considered as a map from integers to integers, well, this is a bijection. When I have this map given by the same formula, but considered as going from natural numbers to natural numbers, well, this is only an injection. It's not a bijection. So now when you take the Hilbert space L2 of Z, then this formula, which is given on the basis labeled by integers, will give you a unitary. But if you consider L2 of n, you consider the same unilateral shift mapping the Hilbert space basis element En to En plus 1, but it will be just an isometry. It will generate the Teplitz algebra. Okay, you'll have at this isometry star type. It's isometry, so itself star times itself is equal to identity, but not the other way around. Okay, so this is a similar effect. Okay, but we don't have to focus on paths that are only finite or going to plus infinity. We can just as well consider paths going to minus infinity. Let me delete this highlight so that it is no longer here. Oh. I want to delete. Yes. Are there any questions? Nope. Okay. So now let's draw some conclusions. This is an almost immediate corollary of this theorem. If E is a graph with n edges and no loops, then there are at most n choose k different paths of length k, which is between 1 and n. All right. So this is already a much better estimate, because n choose k is typically much less than n to the power k. You just look, the n choose k is already limited by n factorial. So, well, anyway, if you just compare n choose k with n to power k, you see that n to power k is typically much bigger than n choose k, right? So we already made a big progress with having an optimal estimate for a graph with n edges and no loops. Okay. Maybe I will make this annotation. Note that n power k is typically, and how I will write n choose k. Oh, well, in words, n choose k. I don't want to do this number theory right now, but I think that this is a very plausible statement. You can play with numbers and see that this is the case. Okay, so we delete highlight and see how we really prove this corollary. Okay, so assumption that there are no loops, that implies that edges cannot repeat themselves in any finite path. That's already been done in around formula 1.1, which I can now recall. That's again the advantage of using the PDF file. We should have a formula 1.1 somewhere here. Yes, it's right here, right? Vice versa, if there are no loops, then edges in any finite path cannot repeat themselves, okay? So this means that there are, so first we cannot have edges in a path when we have no loops. We cannot have edges in a path that repeat themselves, right? In any finite path. Now, so that's using essential part of the proof of the theorem proved last week. So at this stage, we can say that our estimate is n choose k times k factorial, because the edges cannot repeat themselves in a path. But if we don't know that we cannot permute them into a path, then we have to multiply this n choose k by k factorial. However, because of the theorem that we just proved above, we can actually conclude more, which is exactly what this corollary states, that by the Bar theorem, there is at most one way these k different edges can form a path. So since there is at most one way, well, we have our corollary. We can conclude that for a graph with n edges and no loops, there are at most n choose k different paths of length k. All right? But this estimate already much better than n to the power k is still far from being the optimal one. And now, instead of proving from the start the most general statement or phrasing the most general conjecture we have at this moment, I want to do it step by step. I want to do some experiments, some hands-on classification of graphs and counting paths of a given length, so that you gain an intuition. I know that this is a lengthy process, but we are not exactly in a hurry. And I don't want just to show you proofs. I want to show you how these proofs are derived, how we come up with them. So it's going to be very elementary, but I hope it's also going to be very convincing and easy to memorize. So let's look at some special cases when we count the number of paths of length k in a graph with n edges and no loops. Okay, So take any graph with n edges and n at least one. So we don't want just to have a graph with vertices alone. And when we look at how many paths of length 1 we have, then of course we have exactly n such paths, n edges, and we can write n as n choose 1. So as long as paths of length 1 are considered, then actually this estimate is optimal. It's n choose 1. And it's optimal because obviously, I mean, this is yeah, it's simply optimal because I know that the number of paths of length 1 is the number of edges. So this is a tautology, okay? But now, how about the opposite extreme? What if we want to count the paths of length n in a graph with n edges? Again, it's a tautology because I can construct a graph with n edges, which looks precisely like this one. So this is just given by, oh, I don't know how to highlight the picture. So it consists just of n edges assembled into a path. So there's exactly one path of length n, okay? And there is no other way to do it. So in a graph with n edges and no loops, there are at most n over n equal 1 path of length n. And of course, the estimate is optimal because for this graph, indeed, we have such a path. Of course, I could also scatter the edges around and there would be 0 paths of length n. But there are at most n choose n paths of length n, which is 1. And indeed, the bound is optimal because for this graph, it is precisely the case. So this is for the very trivial extreme cases of the shortest possible paths that are of positive length and the longest positive paths. So 1 and n. But the situation is getting already more interesting when we consider something in between. And for starters, I would like to take a small n. How do I highlight it? Okay. Now I want to convince you that there is no graph with 3 edges and no loops that enjoys 3 choose 2, which is equal to 3 different paths of length 2. By simple hands-on classification, I want to convince you that there are at most 2 paths of length 2 in any graph with 3 edges and no loops, okay? And now let me try to do it on a whiteboard, because I think that this is the part where I don't have to write much. And my reasoning might be a little bit clear when I draw while I speak. Okay, so please bear with me. I'm trying to share new, whiteboard, share, clear, all drawings. All right. So the idea is the following. Well, we have 3 edges, and what are all possible ways of arranging them to maximize the number of paths of length 2? Well, of course, we can already disregard all graphs that have 0 paths of length 2 and consider only graphs that have at least 1 path of length 2. And this is going to be our fixed starting point. So I have E1 followed by E2. And this is our assumed path of length 2 that we have in our graph. So what we can play with is the edge E3, which we can try to attach to our given path of length 2 in all possible ways. and see how it goes. So first, what we can do, well, we can simply not attach it. E3 can be somewhere else. I will not write E3. The third arrow will simply be the edge E3, okay? Well, then, of course, we still have only one path of length 2. Because if the edge E3 is not connected to a path, it will not increase the number of paths of length 2. So that's not a good idea. Erase it. Erase. Okay. Now, if we attach the beginning of E3 to the end of E2, then we have three possibilities. Either the end of E3 can end somewhere else outside of the path E1, E2, or it can end at one of the three vertices that are inside the path E1, E2. But please note that if the end of the edge E3 would be anywhere in the path E1, E2, we would get a loop. All right, this would be a loop, this would give us a loop, and this would give us a loop. Okay, so this means that if we attach the beginning of E3 to the end of the path E1, E2, well, then the end of E3 simply must be somewhere else. There's no other way. And now you can see that in such a graph, we have two paths of length 2. E1, E2 is a path of length 2. And of course, E2, E3 is a path of length 2. So now you can see how difficult it is to write with the finger. I can write some simple things, but I wouldn't be able to write a lecture on the whiteboard just using my nails or my fingers. Okay, so now let's consider another possibility. Again, we have our given path E1, E2, and we are wondering, well, let me put it at a different place. So E1, oops, E1, E2. And now we consider attaching the beginning of E3, say, to the middle vertex of a path E1, E2. Again, when we consider all possible places where the edge E3 might end, well, first, it might end somewhere else outside of the path E1, E2, then it's fine. Again, we get two paths. We get the path E1, E2, we get the path E1, E3. Well, we can also attach it to the end of E2. So this would give us such a graph, E1, E2, and this is E3. That's also perfectly all right. And again, we have two paths of length 2, E1, E2, and E1, E3. But we cannot attach the end of E3 to any other vertex in the path, because then we would get a loop. Okay, if we do this, we have a loop. If we do this, we also have a loop. Which means that when we want to attach the beginning of E3 to the middle vertex of the path E1, E2, these are the only two possibilities that do not create a loop and increase the number of paths. Okay, so here we have E1, E2 as a path and E1, E3. Okay, now how about the third situation where we attach the beginning of the edge E3 to the beginning of a path E1, E2? Well, if the end vertex of E3 ends somewhere else, that's fine. Again, we have two paths of length 2. Oh, sorry, no, sorry, I take it back. I take it back. That's allowed. We don't have a loop, but in this graph we still have only one path of length 2. So this is not good if it's attached here, right? If the end if the end of E3 is beyond the path E1, E2. This is no good because we don't create a new path. We still have just one path of length 2. So we erase it. This is no good. Well, what if we attach it to the beginning of E1? Well, it's no good because then we have a loop, right? So this situation is also no good because then we have a loop. Okay. But what if we attach it? What if we attach the end of E3 to the end of E2? Well, we don't have a loop, but again, we have only one path of length 2. So this is no good. Which means that basically we are left with just one option, that is to attach the end of E3 to the end of E1. And this is perfectly legitimate because now we have two paths of length 2, namely E1, E2, which was there from the start, but also E3, E2. So again, we have only two paths of length 2 in our graph with 3 edges. Okay. Now, this was about attaching the beginning of E3 to a vertex in the path E1, E2. We can now consider the other option where the attachment is by the end of the edge of E3 and the beginning is just floating around. And this is perfectly legitimate. It gives us two more cases. Let me clear all drawings. So again, we have our base path E1, E2. And we already considered all possible cases in which we attach E3 to the path E1, E2 by its beginning. So now let's consider the case where the beginning is not attached to the path E1, E2, so it's somewhere else, it's outside. And we connect the edge E3 to the path E1, E2 via its edge. And basically there are 3 ways to do it, of course. If we do it like this, well, there's no loop, but we still have only one path of length 2. So this doesn't work. However, the other two options work. If we attach the end of E3 to the middle vertex of the path E1, E2, well, then we get, again, two paths of length 2, E1, E2, and E3, E2. And also, if we attach E3 to the beginning of E1, well, it also works. Because again, we have two paths of length 2, E3, E1, but also E1, E2. And we are done. We have considered all cases. So this is a kindergarten-like combinatorics that proves that in a graph with 3 edges and no loops, there are at most 2 different paths of length 2. And 2 is strictly less than 3 choose 2, which is equal to 3. Okay. So this proves that our estimate is in general not optimal. We have to do slightly better. Okay. Now let me go back to this, well, not slides, but the file. So I kill this one. I go to share, new share. Go back to my lecture notes, share. Okay. So we are done with this part, and here we have all the cases of graphs where you have no loops and you have at least and by our classification also at most 2 paths of length 2. Okay, so this is the summary of my drawings from the whiteboard. Now I should delete somehow the highlights. Yep, delete. And now we can slightly increase the difficulty of our game. And we no longer assume that our graph has only 3 edges. Our graph has n edges, but at least 2. Of course, we assume that there are no loops. And we can prove the statement, but now for paths of length n minus 1. So the claim is that by a very similar reasoning to the one we did for n equals 3, yeah, if I take n equals 3, then considering paths of length 2 is exactly considering paths of length n minus 1. We have the same result, that there are at most 2 different paths of length n minus 1 in a graph E with n edges and no loops. Okay? And the reasoning is completely analogous, but I still want to go through this. I want to take it slowly so that you develop some intuition of how this combinatorics works. Of course, we can have a graph where all edges are scattered around and there is not a single path of length n minus 1. But we are not interested in such graphs, as we want to maximize the amount of paths of length n minus 1. So let's assume that we have a graph which has at least 1 path of length n minus 1, which means that we have the following path from e1 to n minus 1, exactly as before when n is equal to 3. And now the only graphs which we're interested in, the only graphs that can have more than 1 path of length n minus 1 are graphs with such a path and the edge en attached somewhere. And again, very much as before, we consider all possibilities of attaching the edge en to the given path from e1 to en minus 1. Note that I can do such claims because remember, edges in the path cannot repeat themselves. We have no loops and we cannot rearrange them. So basically, if we have a path of length n minus 1, it really must look as in the picture. Okay. All right. So I think I will not go to the whiteboard right now because the reasoning is completely analogous. I can just do it by considering pictures in the file. Somehow here I decided first to choose all possible attachments of the end of this additional edge en to the given path from e1 to en minus 1. Well, so first, if we decide to attach the end of en to the beginning of e1, the only possibility for the beginning of en is to be outside of the path. Because if we attach the beginning of en anywhere, we have made the beginning of en to be one of the vertices in the path from e1 to en minus 1, we will always get a loop, right? So that's the only possible way where we attach the end of en to the path without creating a loop. And we achieve our goal of increasing the number of paths of length n minus 1, because there are obviously 2 paths of length n minus 1. The one that was there from the start, from 1 to n minus 1, and the new one, which is en, e1 up to en minus 2. Okay. Now, if we consider the situation in which the end of this additional edge en is in the second vertex of our path from e1 to en minus 1, well, then here we have already 2 cases. We can either have a beginning of en floating around outside of the path, or we can attach it to the beginning of the path. In both cases, we do not create a loop, and in both cases, we again have exactly two paths of length n minus 1. And we cannot attach the beginning of En anywhere else, because then we would create a loop. Now, in general, when we attach the end of En to the end of Ej, then there is only one way in which we do not create a loop and increase the number of paths of length n minus 1. And this is exactly what we have on the picture. If we attach the end of En to the end of Ej, and also we attach the beginning of En to the beginning of Ej, well, we have a graph, which is right here, which has exactly two paths of length n minus 1. One when we have Ej inside, and one when we have En instead of Ej inside. And attaching the beginning of En anywhere else either does not increase the number of paths of length n minus 1. Well, if we have the beginning of En outside of a path, or where we have it attached to the beginning of Ei with I strictly less than j, well, then we simply do not have this second path of length n minus 1, because whatever new path we create, it's too short. It's shorter than n minus 1. And if we attach the beginning of En to the beginning of Ei with I strictly bigger than j, then we obviously create a loop. So either we don't create an additional path of length n minus 1, or we create a loop. That's the only situation in which we don't create a loop and we create one additional path of length n minus 1. And then finally, what happens when we attach the end of the En to the end of En minus 1? Well, we have exactly the same reasoning as before. What we have in the picture is the only situation when we do not have a loop and we have an additional path of length n minus 1. And now we consider the other situation in which we attach the additional edge En to our given path from E1 to En minus 1 by the beginning of the end, not by the end. Well, and you can see that attaching the beginning of En to the beginning of Ei with I less than n minus 1, well, it will not create a path, a new path of length n minus 1, when we assume that the end point of the En is outside of a path. So if the end point is outside of a path, the only place where we can attach the beginning and create an additional path, a new path of length n minus 1, is to attach it to the beginning of n minus 1. Because otherwise, we will, yes, create a new path, but it will be shorter than n minus 1. Okay? Then we can also attach it to the end, and we can also attach the beginning of En to the end of En minus 1. And again, we get an additional path of n minus 1. One will be given and another one will be from E2 to En, of course. And that's the situation where the end point of the En is not attached. And we can do it because, well, they considered all situations in which the end point of the En is attached. So we are interested only in the situation in which the end point of the En is not attached. And the only two ways of doing it to increase the number of paths of length n minus 1 is to attach the beginning of the En either to the beginning of the N minus 1 or to the end of the N minus 1. And this is the complete classification of all possibilities. And in each of the above cases, note that we have exactly two different paths of length n minus 1, which proves our proposition. Now, do you have any questions? I know that this is kindergarten-like combinatorics, but I hope it's enjoyable. Any questions? Nope. So now let's prove something even more general. So for starters, we considered just 3 edges and paths of length n. Then we considered n edges and paths of length n minus 1. So this is already generalization. Now, what I want to consider is again n edges, of course, all the time, n edges, no loops. But I do not assume my k to be equal just to n minus 1. I simply assume that my paths are longer than n half. More precisely, I assume that k is bigger or equal to n minus k. And then I claim that under this assumption on k, there are at most 2 to the power n minus k different paths of length k in E, and the bound is optimal. So in particular, we'll recover the previous proposition, because for k equal to n minus 1, we have n minus, in parentheses, n minus 1, which is exactly 1. 2 to the power 1 is 2. Okay, so we generalize the previous proposition from k equal to n minus 1. And obviously, when k is equal to n minus 1, when n minus 1 greater or equal than n minus n minus 1, simply means that n is greater or equal than 2, which is exactly what we assume, right? So that satisfies the assumptions of our proposition. Thus, our proposition 115 generalizes the just proven proposition 114. And now the proof is finally slightly more interesting than hands-on classification. There is an abstract argument involved, so it's getting more interesting, I hope. I just wanted to convince you that in some extremely simple cases, you can prove your claims by the most simple-minded classification possible. Like a child in a kindergarten, you just consider all possibilities and conclude that in all possibilities, you have at most 2 different paths of length n minus 1. Okay. Now we cannot do it by classification any longer. This would be too complicated, and we are going to use instead a slightly more abstract argument. Okay, so as before, we can always construct a graph with a path P1 of length k. So as before, we will consider that our graph already has a path, call it P1, of length k. And we denote this graph in the picture as the path from E1, E2 up to Ek. Because of course, we are not interested in considering diagrams in which there are no paths of length k, right? Surely we can construct a diagram where we have at least one path of length k. And it really must look like this, because remember, the edges cannot repeat themselves and we can have no loops. So this will be just the most straightforward path from E1 to E2, E2 to E3 up to Ek. So this is all exactly as before. But now, note, please, that then there remain precisely n minus k additional edges that can be used to construct more paths. So just as before, we'll try to obtain new graphs, just to try to complete this path to a graph, maximizing or seeing what is the maximum possible number of paths of length k. But now this is very important, that the number of edges that we are left with is n minus k. When k is equal to n minus 1, then we had exactly one edge left to play with. And the combinatorics was very simple. We could just do hands-on classification. Okay, now we call the set of all these additional edges F1. That's just a notation to make it easier to write things up. Now, no matter how we construct our graph with n edges and no loops, any path of length k is composed out of L edges in F1 and k minus L edges from the path P1. Right? Remember, we must have k different edges to compose a path of length k. And we have 2 sets of edges. one set with k elements, and all these edges are arranged into a path. And then we have the set F1 of all edges which are outside of a path F1, that are not part of a path F1. And we can try to attach them any way we please. Okay, for instance, we can have it as on this picture. We can take, say, just one edge EJ from the path P1, and all other edges we choose from outside of this path P1. And you can see that this way, well, we still can have more paths of length k, because this is one path of length k from E1 to EK. But if we choose k minus 1 edges from F1 and arrange them like this, we'll create another path of length k, which is different from the path P1. And whatever we do with remaining edges is irrelevant. We have already a situation in which we constructed the second path of length k. Now, and here is the crux of the argument. Let me try to scroll down. Okay, so first remember that edges in a path cannot repeat themselves and they cannot be rearranged. The order cannot be rearranged. So the path is completely determined by the choice of k different edges. Okay? And now the essential point is that we can choose some of these edges from F1 and some of these edges from the path P1. But here's the following very important observation, is that once we choose and fix all the edges in F1, all the edges that are outside of P1, then there is only one way in which we can complement the subpaths given by edges in F1 into a path using edges in P1. Right? Because these edges in P1 are already arranged in a path. And if I have a subpath given by edges in F1, it ends somewhere in my path P1. And another subpath of elements given by edges in F1 begins somewhere further on in this path. But there's only one way to join these subpaths, right? Just like on this picture. If I end at this vertex and another subpath begins at another vertex, then there is only one way to join these subpaths into a path, just by taking all edges that go from the beginning of the first subpath to the beginning of the other subpath. There's one way to choose the edges from the path P1 to complement the edges chosen in F1 into a path. That's why any path of length k is completely fixed by the choice of L elements from the set n minus k of all edges in F1, of all edges outside of the path P1. Okay? So note that this gives at most n minus k choose L possibilities for having a path of length k with exactly L edges from F1, right? Because if we decide, all right, we choose L edges from F1 and k minus L edges from the path P1, then by the argument just presented, we have at most n minus k choose L possibilities for having such a path of length k, all right? But note that L can vary from 0 to n minus k, right? When L is 0, it means that we choose absolutely no edges from outside the path, so we just have the path from E1 to EK. Then we can say, all right, I choose K minus 1 edges from outside of the path P1. So I have K minus 1 edges outside and 1 edge inside the path. So the biggest number, of course, and the biggest number of edges, sorry, I said it incorrectly, I take it back, no. So L can be as small as 0. And of course, because the number of all edges in F1 is at most n minus k, because this is the number of all edges in F1, there are no more edges in F minus 1. We can choose L to be at most n minus k, because there are no more edges in F1. And when we choose L to be equal to n minus k, it means that we employ all edges that are outside. And because remember, n minus k is smaller or equal to k, well, it can be also equal to k, then we are done. We just arranged in the path. Well, if it is smaller, then we must supplement it in a unique manner by some edges from the path P1. But anyway, it's clear that we cannot choose more elements from the set than the number of elements the set has. So L can vary from 0 to n minus k. So this means that all in all, there are at most 2 to the power n minus k different paths of length k. Sorry, I should have highlighted all of this. Right, because we sum all possibilities. We take the situation when we choose L, take L edges from F1, and L can be 0, can be 1, and so on and so forth up to n minus k. So we sum up all these numbers, n minus k choose L. And when we do this, this is obviously 2 to the power n minus k. That's just a binomial formula for 1 plus 1 to the power n minus k. And that's it. This is the maximal number of paths of length k, where k is greater or equal than n minus k. And we have n edges and no loops. And now please note that the bound is optimal because we have this graph where we take our n minus k edges and attach the first one to E1, the second one to E2, and finally the nth one we attach to EJ. Remember that n minus k is smaller or equal to k. So either we go all the way to EK, this is in the case when n minus k is equal to EK, or we fall short. And the last edge, En, is attached to some edge which is with an index smaller than k, which is the situation on the picture. And then you can see that this is exactly the number of all different paths of length k. All right? Because you just have, for n minus k edges, you have two options. When you are beyond this n minus k zone, then you have only one option. So you have 1 to some power and 2 to the power n minus k, which is exactly the number we are trying to reach. So it is clear that in such a graph, we have precisely 2 to the power n minus k different paths of length k, right? Which is their conclusion. So first we proved that no matter what kind of graph with n edges and no loops we consider, we cannot have more than 2 to the power n minus k different paths of length k. And now we see that the bound is optimal because we can explicitly construct a graph where the situation takes place, where we have exactly 2 to the power n minus k Sorry, I wrote edges. This is paths. Yeah. You see, I saw a typo right now. It's exactly 2 to the power n minus k paths of length k. But this is a typo of Mariusz Tobolski, not of me. He was typing up the notes in Colorado. I'm only re-editing them. But you see, it's very important that I managed to catch it. Well, and I'm already 5 minutes out of time. And I'm wondering, yeah, maybe let me use, so again, I didn't keep my promise and I extended my lecture, but at least today I will definitely finish it on time, and we begin precise sharply at 2 p.m. So let me use these 5 more minutes to summarize what's happening here, how we can go further with searching for an optimal bound for a graph with no loops and n edges. And here we come to a theorem which we already know from my slides. So we already discussed it at length, but now this is a serious theorem. It requires more work than such simple combinatorics. For me, this is very striking, and to observe that if you consider the combinatorics of long paths which are longer or equal to n half, then the combinatorics is very simple. I mean, I hope you agree with me that this proof, was not a big deal. It's half a page, it's completely clear combinatorics, and it's totally general, right? It would seem that proving the theorem I'm now stating for half of all possibilities for paths which are longer than n half is really easy. I mean, this combinatorics is totally straightforward. There are no tricks. You just look carefully at what you're doing and you come up with a proof. There are no gimmicks, no tricks here. You don't need any special ideas to prove it. But the moment you allow paths that are short, of course, if you have very short paths of length k equal 1, well, you are done, it's trivial. But already when you try to consider all paths of length 2 in a graph with n edges and no loops, well, the combinatorics becomes ghastly. And you need a smarter argument to prove it. But first, let me again phrase the theorem. We take again any graph with n edges and no loops, and we consider k in between 1 and n, and then we decompose it. We divide n by k, and we take the rest out of a division. So lowercase n is the maximal amount of times k is n times k is inside n. So r is by definition a number between 0 and k minus 1. Okay, so you have this decomposition of n into nk plus r, with r being the rest of a division of capital N by k. And now the claim is that there are at most n plus 1 to the power r times n to the power k minus r different paths of length k, and the bound is optimal. And this theorem is based on joint work with Alexandru Chilvasitu. Now we have a much shorter proof, that the proof that we derived that was derived in Colorado, and also with Oscar we have a conjecture of how to make this theorem more general. So in fact, I'm going to spare you the proof, which took me a long time in Colorado to explain. I will just sketch it next time. And today I only want to convince you that this theorem really generalizes the previous proposition. Okay, I like such baby combinatorics, so please bear with me. Yeah, and this is exactly, for the final minute. If I have k which is strictly bigger than n minus k, then when we decompose the n into this division part and the rest, well, I can write n as 1 times k, so my lowercase n is equal to 1, plus n minus k, which is my rest. So you can see now that the formula is very simple, because I have 1 plus 1, which is 2 to the power r, which is n minus k. So it's 2 to the power n minus k. But then lowercase n is 1. So 1 to any power is 1. So we are left with n minus k, which is precisely what was claimed in the proposition. Now, if you choose, if it so happens that k is equal to n minus k, well, then obviously n is just equal to 2k. So that the composition is n is equal 2 times k. So lowercase n is 2, and the rest is 0. So we have that this number, oops, here is a typo. I changed the notation for p and k. Is what? Is 2 plus 1 to the power 0, because the rest is 0. And then lowercase n is equal to 2. And k minus r is k minus 0. So this is k, so it's 2 to the power k. But we know that by assumption k is equal to n minus k. So again, we have 2 to the power n minus k. So in both cases, we recover the proposition. So hence, the preceding proposition proves the theorem for sort of half of the cases. And this is a perfect time to stop. And we resume with recitation classes at 2 o'clock sharp. Thank you very much.